This is the final lecture of Chapter 3, and in this very, very short video, we're going to talk about how to calculate the flow rate from velocity and vice versa. So these are the basic equations. Okay, the idea is a flow rate is going to have some mass, or we can write the mass in terms of moles or in terms of mass, and it is moving, so it has a rate, which means whenever there's a rate, there's going to be a time in the denominator. So we typically write the molar flow rate with the symbol n dot, and it's good to be consistent with these when you're doing your calculations, to try to use the proper nomenclature that's standard. N dot means moles per second. Mass flow rate would be kilograms per second and has an m dot. And note the dot, we put the dot on top because it's a rate. Anything that has a seconds or time in the denominator of the units can have a dot on top. Okay, so the volumetric flow rate is volume per second, and it has a v dot. All right, so we can talk also about the concept of velocity. Velocity is different from the mass per time, but it's the rate that pick a slug of fluid, okay, flowing through the tube. The rate that it that the movement of this head driving through the tube, it has a velocity. Okay, and so it has the typical units of velocity, which would be meters per second. So it's the distance that it travels per time. And when we know the cross-sectional area of our pipe, it could be, a square or flat, or most often it's round. So then the cross-sectional area would be written either pi r squared or pi d squared over 4. So this is the relationship between the velocity in meters per second, and if it's the volumetric flow rate, we take the volumetric flow rate divided by the cross-sectional area, and if it's the mass flow rate, we have the mass flow rate divided by the density times the cross-sectional area, and those are going to be equal to the velocity of the material. Okay, that's pretty much it. So let's talk about the density here of gases. Since we've talked about the specific volume, okay, we can use specific volume in our ideal gas equation. So this is the equation here is written P V hat is equal to RT. You're used to PV equals nRT. Well, we simply put the N, the V hat is volume divided by N, the number of moles. So we've gotten the N out of the equation by incorporating it in with the specific volume. So ideal gases at the same temperature and pressure have the same molar specific volume. Okay, so all ideal gases that are at 0 degrees and 1 atmosphere have a specific volume of 22.4 liters per mole. And we can also change the units as we like. If we want to have it in terms of the SI units, it will be 22.4 meters cubed per kilogram mole. So this is a rule of thumb, okay? Rule of thumb, and this is useful to remember, that when is your gas an ideal gas? Well, if RT over P is greater than 20 liters per mole for all gases, then you can consider it an ideal gas. And if RT over P is greater than 5 liters per mole for specifically diatomic gases like nitrogen or oxygen, okay, which are very ideal in their behavior. So these are rules of thumb, so you can remember that. All right, so let's do the quiz. This is video quiz 3.3. So we have 1.00 moles of oxygen at 60 degrees C and 5 bar is flowing through a 20 centimeter diameter pipe. What is the velocity of the gas in the pipe?